All right, here we go with our second video for section 5.4 out of pre-calculus book. I really try to make my videos as short as possible for you. I try to do 10 minutes or less, but didn't do such a great job in our first half here. Let's see if we can get this wrapped up pretty quickly for you. So this slide that I have up here, I would not recommend writing this curve down. You might want to write something about the definition of a periodic function, but no need to copy that curve. This is kind of just an introduction about what it means to be periodic. We're going to do a lot more with waves that look like this picture in section 5.5. So what does it mean for a function to be periodic? It means that that function has output values that are repeating continuously, and it repeats at a regular interval. So if you take a look at this picture, if I were to, I think maybe an easy place to look would be here at some of the peaks. On my two red dots, that function has the same output value, and actually it occurs later on as well. Now I'm going to put a dot here. That has a repeated value at regular intervals. Okay, so we say that the length of time it takes for those values to reoccur, that's called the period. That's what's highlighted in the blue here. From this point to this point, the function goes through all of its range and comes back to where it started. So again, don't want to get too much into that because that's really what we're going to be doing in section 5.5, but it is important for you to know that these functions are periodic and maybe how to recognize it from an equation. I'll talk more about that in just a second. Whether you thought about it as being repetitive or not, we have explored the fact that sine, cosine, and tangent do have repetitive behaviors. We've explored this as we've traveled around the unit circle. We found that as we made multiple revolutions around, also known as coterminal angles, that we would end up with the same values for sine, cosine, tangent, etc. So we didn't call that being periodic, but that really is what it is. Multiple revolutions are going to repeat that pattern. Okay, these images that I have here, I borrowed these from our textbook. And this one on the left, let's start with that. That one is from page 567. And what they're trying to do is give us a diagram for tangent. So they've highlighted 2 points, point P here and point Q down here. And they're talking about how at those locations, that's how long it would take for our tangent values to repeat. So they used arbitrary angle t radians, but I think if we looked at this picture, we could maybe say that t is about at pi over 4 radians. And we know that the sine value at that spot is root 2 over 2. We know that the cosine value at that spot is root 2 over 2. And that means that the tangent at that spot is equal to positive 1. If I were to go in this quadrant at 3 pi over 4, I end up with tangent being equal to negative 1. So not exactly the same value. However, if I were to travel into the third quadrant, this would be at 5 pi over 4, I end up with a sine value that is negative root 2 over 2, cosine value that is negative root 2 over 2, and the tangent, because it's negative divided by negative, is also positive 1. So it takes this long for that value to repeat. And if you look, that's half a revolution of the circle. That's pi units. That means that the period of the tangent function is pi units. Okay, so keep that in mind. I don't have a diagram similar to this for sine or cosine. Well, and you know my awesome drawing skills. I'm not going to be able to recreate that for you. But if you think about how long it would take for us to come up with, let's say I'm at pi over 6, and the cosine value at that spot is root 3 over 2, and sine value is 1/2. Okay, so there will be some repeated values for root 3 over 2 to happen again. Positive root 3 over 2 for our cosine happens here again, but that's not a regular interval because then it happens, it only takes this far for it to occur again. So we say that an entire revolution is how long it would take for that value to come about again. That means that the period for sine and cosine is 2 pi. All the way around the circle. How long it takes for it to occur again. Versus tangent is just pi. And I want to point that out because this, now I'm in the yellow box, these types of equations are going to pop up especially in our application questions, which we're going to do some next. And I want you to know what this language is referring to. So this says sine of an angle. I hate that pink pen, sorry. Sine of an angle, or adding 2 pi radians to that angle. So that would just mean go around the angle again. That's giving us a coterminal angle. So the sine value at that particular area is going to be the same value as the sine of the original. So notice 2 pi. That is because that is the period for sine. Same idea for cosine. And you'll notice that it changes a little bit for tangent. Only takes pi radians for us to get back to the same value for tangent. And again, that has to do with sine divided by cosine being positive in the first quadrant and being also positive because of negative divided by a negative in the third quadrant. So your takeaway from this slide should be that the period of sine is 2 pi and that the period of cosine also 2 pi, period of tangent is just regular pi. And we'll do more with that later. I want to finish with you at the end of the assignment. I have some application questions. They're right out of the textbook. I will say that you really don't have to understand much about sine and cosine to solve these questions because they're mostly plug and chug, but I wanted to go through at least one of them together. I'm going to do number 44 from the textbook. It says the number of hours of daylight H on day T of any given year. And then they're telling us that on January 1st, T equals 1. So at T equals 1 is the start of a new year. This is in San Diego, California, and it can be modeled by this function. So this equation tells us the number of hours of daylight on a particular day. Input is number of day. Output is going to be hours of sunlight. Part A in this question, March 21st is the 80th day of the year. It's the spring equinox. Find the number of the hours of daylight in San Diego on this particular day. So they are telling us the 80th day. That means that T equals 80. We want to find the number of hours of daylight. So we should be finding H of 80. I'm going to rewrite the equation. Only I am going to replace my T value with 80. My input value was 80. All right, just some plug and chug here. 80 divided by 80, that's going to be 0. 0 times anything is 0. So let me rewrite what I have. 2.4 times sine of 0. I'm finding sine of 0. Think about your unit circle. Here's 0 radians. That means that that value, sine, y value, is going to be 0. 2 plus 2.4 times 0. That's 12 plus 0, or 12. 12 hours of daylight on March 21st, which is the start of the spring equinox. Let's do part B. On June 21st, that's the 172nd day of the year, it's the summer solstice. And in the summer solstice, the day, that's the maximum hours of daylight in a day. Find to the nearest tenth of an hour the number of hours of daylight in San Diego on this day. We are using a T value of 172, and we're being asked to find the number of hours of daylight on that day. Again, I'm just going to start with my setup. 12 plus 2.4 times the sine of 2 pi divided by 365. 172 minus 80. I just want to double check that real quick before I move on. Okay, so some plug and chug here. Order of operations, I'm going to start in those grouping symbols. I would do my subtraction first. That ends up being 92. When I do that, the next thing I'll do is multiply 92 by 2 pi divided by 365. And let's see, I did that on my calculator earlier, and when I did that, I got 1.5837, etc., but I just left it in the calculator. Okay, next you want to make sure your calculator's in radian mode. And and plug and chug here. Next, I would take the sign of that answer. Then I'm going to multiply that by 2.4. And when I did that, I got about 2.399, etc. Next, I'm going to add those together, so that's 14.399, etc. They asked us to round to the tenths place, so 14.4 is the value of h of 172. So at the summer solstice, we have about 14.4 hours of daylight. All right, that finishes section 5.4 there, gets us through our periodic functions and our applications, and we're going to do more with those periods when we do our graphs in section 5.5. Thanks, guys.